one of the things that you need to know in electricity questions, almost all electricity questions, even if you have not been asked, is Kirchhoff's laws, both of them, first and second law. Now, I'll read this question. A battery of electromotive force, EMF, 9.6 volts, and a negligible internal resistance is connected in series with two fixed resistors and a thermistor, as shown in Fig 7.1. Now, why are they saying series? In this case, don't they see this voltmeter here and this branch here? Now, the issue is this one. A voltmeter is usually considered to have a very high resistance such that current will never choose, will flow, let's say, from the battery like that. But when it comes to this junction here, all of the current will choose to go where there is less resistance. Since the resistance of the voltmeter is considered to be infinite or to be very high, no current will consider to go through the voltmeter. So we don't even consider, even though the voltmeter is in parallel with this and this. As far as sharing current is concerned, we don't even consider it to be sharing current with these resistors. So the current going through these resistors, the thermistor and the 3400, it is the same current going through the 5800. So that's why the 5800 resistor he has been referred by this question here that the battery here is connected in series with the two fixed resistors. The fixed resistors that are considered are this resistor and this resistor, and a thermistor. This is the thermistor that is being considered. So this is the language that they are showing. They are considered to be in series even though there's a voltmeter, because they know that the voltmeter can behave as if it is not part of the circuit. It is in parallel, but it can behave as if it is not in part of the circuit, as current relatively avoids it. Okay, so now let's continue with our reading of the question. The fixed resistors have resistance 3400 and 5800 ohms. The reading on the voltmeter in the circuit is 6.0 volts. Calculate the current in the resistor of resistance 5800 ohms. So all the times we want to know the current in the resistor of 5800 ohms. We don't even know the resistance of the thermistor. We know the what do we know? We know the voltmeter reading. The voltmeter reading is telling us the voltage across in total the 3400 ohms resistor and the thermistor. So, but yet we don't know the voltage. We don't know anything else other than that. So here, what do? We use Kirchhoff's laws. In this case, we use Kirchhoff's second law. Every time we know Kirchhoff's second law. What does it say? It says that in a closed loop, the algebraic sum of the EMFs equals to the algebraic sum of the potential differences. Okay, so suppose we choose, not like we have an option here, this is our closed circuit. We can see that in this loop we have an EMF of 9.6. We don't have another EMF in this loop. Okay, so we now need to add all the potential differences in this loop. So we don't need to worry about the potential difference across the 3400 resistor and then the thermistor, because we know that the total voltage across them as given here is 6 ohms already, 6 volts, sorry. So the potential difference across them is 6 volts. Plus then, of course, we don't know the current going through the other remaining resistor that is here. But we know, according to Kirchhoff's law, that its potential difference then would be I times 5,800, sorry. So we have applied Kirchhoff's second law, as you can see. So then we'll take our 6 volts to the other side. When we subtract 9.6 multiplied minus 6 volts, we'll get 3.6. So I 5,800 is equals to this. So then in conclusion, we divide both sides by 5,800, and we'll get that our current here is 6.2 times 10 to the power of minus 4. So that's our current after dividing both sides by 5,800. So what did we just do? We used